Today we're going to just do a quick review of gravitation and talk about an application of angular momentum with orbits. So the first page here, and again, these are supposed to be lecture notes, and the red is what we were going to discuss in class. I just want to take a quick review of gravitation because I think it's important to stick that in there. So the idea of when we talk about a conservative versus a non-conservative force, and you can read through these bullet points here, for the definition of a conservative force. The conservative forces that we have focused on in class have been gravitational forces and elastic forces, and this whole idea about the work being done by a conservative force. Non-conservative forces would include resistive forces. So basic definition of work done by a conservative force, again, if we look at these bullet points, is that it's equal to the negative change in gravitational potential energy. So that's kind of our working definition here when we're dealing with conservative forces. And if we remember that the work done for an object is a dot product between the force applied dotted with the distance over which that force is applied. And if we remember, a dot product means we take the magnitude of the force times the magnitude of the distance times the cosine of the angle between them. So the rest of this page is just the derivations of the work done by gravity, one for a constant gravitational force and one for, a constant gravitational field, the other for the varying gravitational field. That one was a little more challenging to go through. And this statement right here, this integral here is basically if I have a path that is not just a straight line path, but I have something that's curvy, means if I want to figure out the total work done over this random path, I can break the path up into tiny little segments dr, and if I add up the work done over all the little tiny drs, then I'm going to get the total work done by the conservative force. So that just kind of takes you through. This is for the constant field, and then the gravitational potential energy due to a varying gravitational field. There's a video on this that I had you guys watch before. He's very good at taking you through the calculus of it, but basically the two ways, assumptions when we look at this gravitational field and knowing when to use it, is this idea that you're told that treat gravitational potential energy to be zero at infinity. And you can kind of review our reasoning behind that. I don't want to spend too much time going through this. But the bottom line is the derivation of this equation, which is on the equation sheet, which is a new definition of gravitational potential energy. And when do you use it? When you have like satellite systems, orbits, or if you're told, assume this. So coming up with that. So, and then just kind of quick reviewing from that definition of work done by a conservative force, that if I take the negative derivative of that potential energy function with respect to the distance, then I get that force. So, and then we had the graphs that we talked about. This position right here represents the surface of the planet. So I have it as radius of the Earth. So everything to the left here is inside the planet, and outside the planet is over here. So we saw this linear function with the force of gravity, and this graph could easily be the gravitational field as well. And then we have this flattening out that goes as 1 over r squared. But again, we see our gravitational potential energy, our gravitational force going to zero as r goes towards infinity here. And similarly here, again, this, if I take the derivative of this function, I'm going to get that function. This is going to be a parabolic here, and this will go as 1 over r according to this equation here. Again, gravitational potential energy increasing, but increasing to zero. So that was just a quick version of that. Okay, but what I really wanted to focus on was looking at how to calculate orbital speed of an elliptical orbit. And there are two methods to use this. One is using conservation of energy, and we're going to find the better choice for elliptical orbits is going to be using conservation of angular momentum. So we do know that mechanical energy will be conserved in an elliptical orbit where our system is the sun and the planet. The sun and the planet here. So you have kinetic energy and gravitational potential energy. So this represents the total energy at position A, and that is going to be equal to the total energy at position B as it orbits around. Substitute in our expressions for kinetic energy and for gravitational potential energy, and you could see if you were asked to solve for, say, the velocity at A, if you were given this velocity, it's a bit of a nightmare. So you could do it, but it's not that easy, so you don't. What you do want to use is conservation of angular momentum. So if I look at angular momentum, the only force acting on my system, if my system is just the planet here, is that gravitational force that is pulling it towards the sun itself. So if this is a sun system, and that force passes right through the axis of rotation, so there's no net torque. So by definition, no net torque means angular momentum is conserved. So the equation for the angular momentum is much more simple than looking at a conservation of energy. So if I set the angular momentum at position A equal to the angular momentum at position B, and remember the sign of the angle represents the angle between this radial vector and that momentum vector, and if we see, that's a 90 degrees. So it gets even more simple, and we can just kind of look at this equation and compare it to that and say, ooh, I don't want to do that. I'd much rather do this. So just a word of caution when using this is if you're at any other position. So if I was over here, say like position C, again, that angle between the radial vector and the momentum vector will no longer be 90 degrees. So you have to make sure that you keep that sign term in there. So just a word of caution. And then here's the link for the video. I had you guys watch this video when we were doing the energy unit, but it's a great review of orbits and gravitation. And if you're interested, the angular momentum gets briefly discussed at about the 14-minute mark. All right, you guys have a good day.